All right, so in this last video, I just want to go over how to work two more practice problems with conservation of energy. Um, Yesterday we worked one, I recorded the video yesterday. In part one video, maybe it was part two, I think it was part two, I recorded a video about dropping some cheese. This one is about a girl on a swing, and there's one at the bottom that is about a roller coaster, this roller coaster here. So let's look at how to do these. This one says 42 kilogram girl. First thing to notice is they do give you her mass here, but remember, you don't need it. Sometimes you'll be given the mass, sometimes you won't be. You never need the mass. If you put it in there, you're going to get the same answer. It doesn't change anything, but it's just more work. So I'm not going to worry about that 42. At her highest point, she's 2 meters above the ground. And the question says, how fast is she going when she is 0.85 meters above the ground? So how fast is she going? We want to know speed right there. And there's a height that's given here, and there's a height that's given here. Let's go ahead and draw a picture of what's going on. But before I draw the correct picture, I actually want to show you what the incorrect picture would look like. So many people would draw a picture that looks like this, okay? And they would say, well, this is EI, this is EF, and they would reason that it's potential energy at the top, kinetic energy at the bottom, and then they'll say, when we write down EI equals EF, again, don't write this because it's not correct. They will say that mgh at the top equals mv squared over 2 at the bottom. Get rid of the mass, solve for the speed. Which is great if the problem says how fast is she going at the bottom, but it doesn't say that. It says how fast is she going when she's 0.85 meters above the ground. To be clear, at the bottom, her height is 0. That is not where this problem says she is. She is somewhere in between, where she still has some height. So we need to be careful about recognizing that kind of stuff. So the correct picture to be drawn here, is this even focused? Oh, that's better. The correct picture that we would draw here is something like this. The top is correct. There's EI. It is potential energy at the top. But she's not all the way at the bottom. The EF point is going to be somewhere in the middle. And the energy in the middle, it's not potential, it's not kinetic, it's both potential and kinetic. She still has height at that point. I'll give you her height right there. It wouldn't even be a bad idea to write this down. Height right there is 2 meters. Height right here is 0.85 meters. There's a height at both places. And we want to know how fast she's going at that point. So when we write down EI equals EF, that's where it starts from. But again, remember, what comes next, what we write next, must be determined by the decisions we made in the picture. We draw the picture to understand what's going on in the problem. So if you don't make these decisions about what kind of energy is going on and where it is in the path that the problem is talking about, you cannot go on with the rest of the problem. You can't do it. So EI, I'm going to look over here, EI, we decided it was potential energy. So I'm going to write MGH. That's where it came from. EF, I'm going to look down here at EF. We decided EF was both forms of energy, PE plus KE. So PE is MGH plus KE is MV squared over 2. Again, this decision that I made is where I got all of that right there. Hopefully that makes sense. And once again, like any of the other ones, even though there's two masses on the right side, we can still get rid of the mass. This is a really important thing to understand. It doesn't matter what is going on in the problem. All conservation of energy problems, which all start this way, mass doesn't ever matter. If you're wondering about, well, there's 2 over here, there's 1 over here. Yes, we can factor the mass out of both terms here, and then we have 1 on one side and 1 on the other, and we can get rid of it algebraically. So now we can plug in numbers, but before we do, it's useful to remember that we're trying to find V. I might even circle that that's what I'm looking for. 9.8 here. These two H's are not going to be the same. This H is the one at EI, which is 2. And the other one, 9.8 is G there. The other one is our height at the bottom, or not at the bottom, but in the middle of the swing path is 0.85. V is what we're trying to find. I'm going to leave it as a V over 2. So let's clean this equation up a little bit. 9.8 times 2 is 19.6. 9.8 times 0.85, if you do that, I believe, is 8.33. Still got my V squared over 2. All right, a couple of things that some people forget about. When you're doing arithmetic, maybe I should write this down. You should write this down, because a lot of people struggle with this. When you're doing arithmetic, which means no solving for variables. It's just math. It's just numbers, right? Maybe I'll write that, just numbers. When you're doing that, when you're doing arithmetic, we have to use the order of operations for PEMDAS, right? Parentheses, exponents, and then multiply, divide, doesn't matter the order you do those in. Add, subtract, doesn't matter the order you do those in. You do that this way when you do arithmetic. But when we're actually doing algebra, when we're solving, right, solving for a variable, when we're doing algebra, it's like PEMDAS in reverse, right? So when we do PEMDAS in reverse, we would go, this is kind of fun. PEMDAS in reverse. So you actually do your add subtract first, then your multiply divide, then your exponent, and really truthfully we probably would put the parentheses at the front. Right, so that's always got to be done first because of what parentheses means, but in terms of these operations. But we don't have any parentheses in this problem, so that doesn't matter anyway. So we're going to do our add subtract first. This is multiplication. I would have to multiply by 2 to get rid of that. I'm not going to do that first. I'm going to subtract the 8.33 to get rid of it on the right side. When you do that, you get 11.27 equals V squared over 2. Pull that down. Now I'm going to multiply by 2 to get rid of it on the bottom on the right side. Do the same thing on the left. 2 times 11.27 is 22.54. Still have my V squared left. Last thing I need to get rid of is the squared. I do the opposite, which is square root. And you get a speed of 4.7 meters per second. To be clear, this will be the hardest type of conservation of energy problem that I will expect you to do in class because of the two forms of energy here. It could be on either side. It could be two forms of energy for EI, could be two forms of energy for EF. We could also technically do both equals both, but I'm not ever going to actually require you to do those just because those are a little bit longer. So if you can do this, if you can recognize this, and the most important part of this, by the way, is simply recognizing that there are two forms of energy. If I can see that you recognize that, that's what I really want to know. That's what I really would like to see that you understand how to do. While we're on a swing, let's go ahead and look at the graph for swings, for pendulums. Remember, when we draw graphs and when we analyze them, the first one to understand is that the total energy line is always at the top and it's always going straight across, which means that line doesn't really tell us much about what's going on because it looks the same for everything. The second line that we look at is the potential energy line, because remember, the potential energy follows the height. So if this is the most amount of energy and this is the least amount of energy, TB means top, bottom, the top of the pendulum. So this is a pendulum swinging from top to bottom, top to bottom, top to bottom, etc., going back and forth. So I'll do the potential energy line next. The potential energy at the top is high because it follows the height. And when the pendulum comes to the bottom, potential energy is 0 again. And at the top, it goes back up. At the bottom, it comes back down. So the line for potential energy would look something like this. Something like that. I'll label that potential energy. So total energy is always at the top and it follows the height. Sorry, total energy is always at the top. It's always a straight line all the way across. Potential energy follows the height, which means the potential energy many times looks like what's going on in the scenario. And potential energy is going to be a reverse image. I mean, literally, if you think about this image right here and simply flip it over, that's what kinetic energy is going to look like. So instead of at the top, kinetic energy at the top is 0. Kinetic energy at the bottom is very high because that's when the pendulum is going the fastest. So we'll go up down, and up again. And that's our line for kinetic energy. Again, a reverse image of potential energy. All right, let's go down to the bottom and let's look at this roller coaster. If you have a graph for this, let's look at this graph. If yours is not there, just go ahead and draw a graph that looks like this. Let's draw the graph for the roller coaster the same as we did for the pendulum, and then we'll look at this problem down here. It's an easier problem. First line, total energy. This is 0. Total energy is whatever it's going to be, whatever the top energy is going to be, some number. Total energy always looks the same no matter what kind of problem we're dealing with. It always stays the same for conservation of energy, and it's always at the top. The next line I'm going to draw is potential energy. Potential energy follows the height. We have to remember that. And in a roller coaster, it's really, really fun. And I'm actually going to start at this point right here. I'm not going to worry about any of this stuff behind it. The potential energy follows the height of what's going on. And so the line for potential energy is actually going to look exactly like the roller coaster itself looks. So potential energy line will go something like that, because the potential energy follows the height. Maybe we could go a little higher right here, but you get the point. And then remember, kinetic energy, we take potential and we simply flip it over. It has to be a mirror image, and the reason why it has to be a mirror image is because kinetic and potential always have to add to the total, which stays the same. So the kinetic energy will be up to the top, down a bit, and up again. All right, so there's our mirror image. There's our mirror image of kinetic energy. And that means, remember, and I think I showed you this before, we're always going to get the highest speeds at the lowest possible points on the roller coaster, on the pendulum, and on something that is that's rising and falling, like this wedge of cheese that was dropped. You always get the highest speeds at the lowest possible points. And the reason is, at the lowest possible point, we have the highest kinetic energy and the lowest, or 0, potential energy. Where we have the highest kinetic energy, we have the highest speed. And that bottom point is actually what we're dealing with right here on this picture. So it says, how fast is the roller coaster going at the lowest, or at the third and the lowest position? So there's my third position. It's right there. I'm going to call that EF, and I'm going to call the one at the top EI. You don't necessarily have to do this problem this way. You could start from this point where we have both forms of energy, but it's going to make the math a little bit harder. We know what we need to know at both of these points, so that's what I'm going to call. If I didn't have this picture there, I would draw this picture, and all I would have to have is just a simple slope that goes down this way. EI at the top, EF at the bottom. I know the top is potential. I know the bottom is kinetic. Right? And we want to know the speed at the bottom. So, simple problem, conservation of energy problems always start the same way. EI equals EF. We decided EI was potential energy, so the formula for potential energy goes here. We decided EF is kinetic energy, so the formula for kinetic energy goes there. And once again, just like always, we don't need the mass. They don't give us the mass anyway. So now we're going to simply plug in numbers. G is 9.8. The height we're starting with is given us right here, actually, is 10 meters. And we're solving for that speed at the bottom. So I'm going to leave it that way. We could go ahead and simplify this. 9.8 times 10 is 98. But I'm going to do that along with the first step of algebra, because the first step of algebra, we actually don't have any add and subtract, but we got to multiply by this 2 to get rid of it, times 2 on both sides. So I got 2 times 9.8 times 10, which is 98 times 2, which gives us 196. Still got v squared left over here, and then we're going to take the square root of 196, and it'll give us exactly 14 meters per second. So we know that this roller coaster has to be moving at 14 meters per second at the very bottom. That's the fastest speed on this particular roller coaster. All right, that'll just about do it for conservation of energy.